Hello, my name is Pavel Kaprov, and today I'll be presenting you my work where we've been streaming data from HAAS CNC machines through MQTT protocol with Sparkplug B specification to enable smart factory paradigm. The main goal of this project is to demonstrate the ability to stream data from machine assets in a unified namespace, particularly when 100 machines of assets are connected on a network within a smart factory. We want to show that one can add a low-cost device such as Raspberry Pi that acts as an edge node and can publish data reported by CNC units. It connects machine assets to a factory-wide network of machine assets while utilizing available standards to structure data from CNC machine. The sub-goal is to demonstrate how data is streamed locally to data historians that are connected directly to the factory network. We have also showed scenario where a local dashboard updates its values based on streaming data from the asset. Also, the second scenario demonstrates how data is streamed to the cloud platform verification and analysis. And the third scenario shows how IIoT enables the development of digital twins. So here you can see schema of our setup on the Fitzwilder Hall lab of NC State Advanced Manufacturing Lab. Most modern manufacturing processes follow the reference model for computer integrated manufacturing, also known as a Purdue Model. The IIoT architecture does not fit this model, especially with big data and machine learning applications. The Purdue Model prescribes 5 layers that separate OT from IT. Levels 1 to 3 are located on the factory floor and are not connected to the internet. The demilitarized zone, or DMZ, at level 3.5, performs the cybersecurity function and air gaps the OT from IT. Enterprise levels 4 to 5 are retrieving only siloed data that cannot directly access the assets on the factory floor. A 5-layered model limits data flow in the context of smart manufacturing and specifically in IT-OT integration in industrial IoT settings. The Purdue reference model also does not allow quick equipment addition and operation. This model does not fit the IIoT paradigm since device assets on the shop floor will need to access cloud-level resources. MQTT Sparkplug B can be applied to the existing Purdue model and allow access to the data from the IT level and send additional data from machine learning predictive systems to the OT level. Conventional methods of industrial communication, such as OPC-UA, mostly use a poll response approach, also known as client-server approach, which may not always be reliable, particularly in scenarios when a poor network connectivity through a wireless connection and non-deterministic number of device assets come on and off the network. On the other hand, publish-subscribe type messaging architecture can alleviate the concern of poll response approach by decentralizing data flow. In MQTT, every machine asset can talk to any other machine asset within the factory floor via broker. Recently, the OPC Foundation released a PubSub model specification to implement the same data structure through other application layer protocols such as AMQP or MQTT. One good known way of accessing the data of metal cutting machine tools is via MTConnect. It is a read-only, royalty-free communication protocol that uses XML and HTTP to request and deliver data from MTConnect-enabled devices. The benefit of this protocol is that it does not require any proprietary software or deep knowledge to access the information from the equipment. The biggest drawback is that someone needs to create MTConnect agents and adapters, which most likely will need to be performed by the original equipment manufacturers. Unfortunately, not all equipment has a built-in MTConnect agents, and even those with it might not give all the information needed, like HAAS MTConnect. The OPC-UA is a machine-to-machine protocol that the OPC Foundation designed specifically for industrial applications. Unlike MQTT, OPC-UA is a server-client architecture that polls the client to get the data. Every device type has its proprietary specification that must be followed to work correctly with OPC-UA servers. Classic OT-IT infrastructure includes various devices connected to the OPC-UA servers that communicate with IT structure. All OT participants should also communicate through OPC-UA servers. The data types that can be transferred through those protocols are also predefined by specification and must completely correspond to the ISA 95 standard. It was shown that there is an issue when one is trying to communicate between different OPC-UA servers or even non-OPC servers. There are several attempts to simplify the use of UA without specific proprietary software, but they require substantially more computational power than MQTT protocol. MQTT consumes traffic only when needed. It is called report by exception and requires only a regular pinging with a zero payload. The header of MQTT message is only 2 bytes, comparing to around 150 bytes in HTTP, which is used in OPC. A typical MQTT network includes at least 2 nodes, a client and a broker. In this scenario, we have multiple clients that are publishing data from CNC machines and robots. It also can have client as a subscriber where we have factory IT historian. Then we can use external cloud systems or even mobile apps. IIoT enabled by MQTT utilizes the pub/sub architecture that secures devices from accessing through network ports. However, the MQTT protocol does not define a standard for how the body of the message is structured, the type of metadata to be transferred, nor does it define the topic level hierarchy. A recently released version of the MQTT Sparkplug B specification addresses some of these concerns, particularly amenable IIoT-based operations. Sparkplug B specification proposes the topic hierarchy, where the namespace is usually SPB v12 or other version. It is followed by group ID. In our case, that was FWH2200, which is the location of our lab. It is followed by message type. As you can see, it can include different messages like birth, death certificates, data, command, or something else. It is then followed by edge node ID. So in our case, we take DData and RPI VF21, which means Raspberry Pi VF21 machine, and the device ID. In our case, it is NGC, New Generation Control, but there can be several devices connected to Raspberry Pi that is located at VF21. In collaboration with industrial partners, CESMII has created a Smart Manufacturing Innovation Platform, or SMIP, to enable frictionless movement of information, raw and contextualized data between real-time operations, people, and the systems that create value across manufacturing processes. Combining new concepts in the context will provide the ability to define new systems without the need for extensive middleware configuration or infrastructure maintenance or management. Various machine assets on the shop floor can publish data to an MQTT broker via topic hierarchy specified by the Sparkplug B specification. Different subscriber nodes listen to specific topic namespaces, pick up the messages, and process them as needed. The subscriber nodes themselves are not directly communicating with publisher nodes. The communication happens only through the MQTT broker topic channels. If industry standards are available, such as MTConnect for CNC machines, you can structure the data sent by the publisher. Devices that might be part of production cell can individually communicate with the broker on the specific topics or collectively communicate to the MQTT broker via production cell specific topic channel. The unified namespace architecture ensures that machine assets do not need to communicate with higher order information systems through specified controlled layers. Rather, a unified namespace is established that allows decentralized machine-to-machine or machine-to-cloud communication, and without the need of centralized nodes that force communication between various levels. MQTT SPB IIoT architecture allows adding any number of new nodes and devices, and it needs only a table from a database to be created before historian starts to make records for the device or node. Such approach enables the vast majority of opportunities for Industry 4.0, and these technologies can be implemented on a production floor. As a result of using CESMII SMIP platform and MQTT Sparkplug B's communication, we were able to create an interactive dashboard that can be accessed from the internet. The data is accessed through Python scripts run locally to utilize GraphQL to write the incoming values to the corresponding tag IDs on the SMIP. The process involves a call to retrieve all tag IDs and their related variable names. The records update occurs only as and when the records are written to the database, thus reducing the delay. Data collected from HASS machines was used to feed into the Fusion 360 Python code that allowed in almost real time to copy the XYZ changes of the CNC machine and represent it in 3D space. Our work is implemented digital twin inside Fusion 360 CAD software, which is not purposed for that, but as already proved a concept, showed the possibility of creating a digital twin using the data available from the unified namespace. Our future work includes implementation of Unreal Engine 5 to create the digital twin of our lab at Fitzwilliam Hall of the NC State University. This work demonstrates how the MQTT Sparkplug B works with HASS CNC machines. Work is still required to translate machine-specific codes to gather data and have it transported to subscriber endpoint. This means information model is required to enable interoperability between various device assets and machine vendors. While information models like MTConnect exist for CNC machines, not all machine types and their associated assets have means to standardize information coding to enable interoperability. The implementation of our approach can be used in retrofitting of equipment. The future work orients towards increasing the nomenclature of equipment types and vendors, like CNC machines, robots, conveyor stations, sensor suites, 3D printers, and others. Existing IT systems do not have functionality of direct access to the MQTT protocol. Thus, it has to retrieve the data from database, which violates the idea of a unified namespace. Future work in this direction is needed to ensure that IT software vendors have the ability to communicate, subscribe directly with the MQTT broker. Sparkplug B has only been released in 2019, and further revisions are available now. We expect that the adoption by the industry can lead to a better implementation of this protocol. So I would like to express the acknowledgement to CESMII's Clean Energy Smart Manufacturing Innovation Institute through its original Smart Manufacturing Innovation Center funded program.